What the Haversine equation does is it finds that angle alpha that's directly over my head. That is the angle formed by drawing a ray from the center of the Earth to your starting location, and then drawing a second ray from the center of the Earth to your ending location.
So let me break down what the Haversine equation is, and then I'll break down the Haversine formula. But first off, Haversine means half sine. And this allows them two 90-degree angles so they can project their math down to a plane underneath a hemisphere. So they'll have two 90-degree angles. Now the Haversine equation is basically just a claim. And what it claims is that the angle measured from the surface of the hemisphere, from the beginning point to the ending point, is equal to, remember equation means equal to, so the angle measured from the surface of the hemisphere from beginning to end is equal to the same angle down on the center of a plane underneath the hemisphere. So really it's just a claim. The reason they do this is because these calculations do not work from the surface of the sphere. They have to go down to the center plane of the hemisphere.
Two rays will form that angle alpha, and that's what the Haversine equation is designed to do. You then apply the Haversine formula to find one of two things, depending on what information you start with. You either find the distance along the surface of the sphere between those 2 points if you know the radius of the Earth, or if you know the distance between those 2 points because you drove it and measured it, you can use that to find the radius.
Yeah, but that would be assuming you're measuring a hemisphere in the first place. And find a significant distance, straight line driving distance in the first place. Bob's just making claims. Haversine uses a radius, or using the distances from a model that already has the radius.
Yeah. Now, in order to find angle theta, what we can do is use a little bit of trigonometry and something called the Haversine formula. Now, the way the Haversine formula works is that we divide this angle in half, right here.
So I wonder why he didn't draw the baselines. He just, I guess he's ignoring it. Well, I'll tell you what, Bob. I'll go ahead and draw them in for you. I'll draw in your two 90-degree angles so you can have your Haversine formula in the plane that you need.
Even though we want angle theta, which is this entire angle here, what we can do is we can solve, and that angle, we'll call that alpha. Angle alpha equals angle theta divided by 2.
So that's basically like saying 2 plus 1 minus 1 equals 2. It's stupid, but technically it's not even theta, because theta, this is the definition, theta is either the azimuthal angle on the xy plane or the vertical angle, which is that angle measured from the z-axis out to the point in question, and he didn't measure from there. He came up with an equation, but technically that's not even a theta. He didn't measure from there.
Angle theta equals 2 alpha. So notice that there's absolutely no radius involved in any of this.
So why would he even claim that? I'll tell you why, because we're going to tell him you need R for that. But what he's going to do instead is use given distances from longitude and latitude lines from said radius. So you need the radius one way or another.
What we're doing is we're employing the Haversine formula to find the Haversine, which we're calling angle alpha, in order to determine what angle theta between the starting point and the ending point in the center of the Earth. Now,
one of the problems that I run into with flat earthers is their inappropriate demands for particular tests or measurements. For example, they only accept physical measurements, i.e. with a tape ruler. They won't accept mathematical determinations.
Not at all true, Bob. We tried 1.22 times the square root of the observer's height in feet to measure your globe horizon, and it failed.
So I got to thinking the other day, what if I could measure the Earth with a tape measure? I wonder if that would be good enough for them. Well, let's find out. Ladies and gentlemen, here is a direct measurement. This is the Southern Cross Cable Network. It is a series of undersea cables between Australia, New Zealand, Fiji, Hawaii, and the western United States. The origin and destination of each of these cables is documented, as is the length of the cable. It goes from Alexandria, New South Wales, to, forgive me if I mispronounce this, but Winnipeg, New Zealand. So how do we determine how far it is on a flat Earth between Alexandria and Winnipeg? Now again, since this is a flat surface, we can use Euclidean geometry.
It's all Euclidean geometry, Bob. That's why you had to transfer your measurements down to the center of a plane projected up to the hemisphere above you, because you can't calculate from the surface of the hemisphere. It wouldn't work, Bob.
If we draw a line from Alexandria to the North Pole and calculate the number of degrees between Alexandria and the North Pole, we can calculate the length of this side of a triangle.
So what Bob wants to do is start flat Earth off at the North Pole. In reality, these latitude angles are measured from the equator, and when they do their angle measurements on the globe, it is observer dependent. So these angles should be measured from the observer, not the North Pole. Now, Gleason's map is centered around the North Pole, but if you're going to use a latitude-longitude coordinate system, then you have to center yourself from the observer, not from somewhere you're not, but from somewhere that you are. And I don't think Bob understands this. But we'll let Bob go ahead and do his math and just run his straw man out to the end, and then we'll go to the AE map online that'll calculate the distance for us, and we'll compare him to Bob's straw man and see if his calculations match flat Earth calculations. Something tells me that they won't.
Now, the coordinates for Alexandria are 33.9 south, 151.2 east. So to get the distance, it will be 90 to the equator plus 33.9 times 111 kilometers. That distance will be 13,752.9 kilometers. Likewise, we can do the same for Winnipeg. The difference in longitude between Alexandria and Winnipeg is 23.4 degrees, so that's this angle at the North Pole. Now, on a spherical Earth, we use something called the Haversine formula. Now, if you thought that the law of cosines was a mouthful, let's look at the Haversine formula. The Haversine of the distance between those 2 points is the sine squared times the change in latitude over 2, plus the cosine of lat 1 times the cosine of lat 2.
So there's your proof that he is doing these calculations from a plane and projecting the calculations up onto a hemisphere, because he's using the sine of latitude 1 times the sine of latitude 2. Well, the latitudes are all calculated from the celestial equator, which is a plane,
times the sine of the change of longitude over 2. Now, once you have the Haversine, we actually need to do a little more to it. To get the distance between the 2 points, you take 2 times the radius of the Earth times the arcsine of the square of the Haversine, because the Haversine is a sine squared. So on a flat Earth, that's how long the cable has to be to go between these 2 locations. Now, on a spherical Earth, the great circle distance should be 2,141 kilometers. We've already calculated the flat Earth distance as 5,651.9 kilometers.
So according to Bob, that city right next to Sydney, out to the coast of New Zealand, on a flat Earth has to be 5,600 and something kilometers. So let's check the online AE map generator. So we center his coordinates right by the town next to Sydney, and we put a total radius of 3,000. So from the center to the edge is 3,000 miles, and we've went clear past New Zealand. So how could it be 5,600 kilometers when 3,000 kilometers goes clear past New Zealand in full? So Bob doesn't understand the way the AE map works, or else he wouldn't be strawmanning like that and making these claims. But let's bring it down to 2,000 kilometers from the center. And there you see New Zealand just barely poking in the 2,000 kilometers. So there's your distance on the AE map on a flat plane. It's more like 2,000 kilometers, or just a little bit more than 2,000 kilometers, because from the center to the edge is 2,000 kilometers, Bob.
What's the actual length of the cable? Based on published records, the cable length between those 2 locations is 2,276 kilometers. Okay, what's this tell us?
It tells us you full of shyster, Bob.
Well, first of all, The minimum distance it could be on a spherical Earth is 2141. If it's anything greater than that, that doesn't rule out a spherical Earth in any way, shape, or form. However, on a flat Earth, the minimum distance has to be 5651.9 kilometers.
Sorry, Bob, but I just used the AE map generator and showed that the flat Earth distance is closer to 2,000, maybe 2,100 kilometers. Pretty close to the distance you came up with all that unnecessary math. But thank you for watching. Please like and subscribe. See you in the next one.